All right, so now we've looked at limits and how to evaluate some. If they're continuous, then it's just evaluate. That's what we want to look at more, is the relationship between the limit and continuity of functions. So like I just mentioned, or we mentioned in the last video, that if f of x is continuous, then continuous at a, some value a, then the limit as x goes to a of our function is the function just evaluated at a. Okay, so that's in the one direction. If we already have that a function is continuous, then or at that place, great. Then we can just evaluate the function, there's no problem. The limit exists, it's the function actually evaluated. Okay, so that's going the other way. But we can actually use the limit to define what it means for a function to be continuous at all. Okay, so we have it this way. We're assuming that the function is continuous, then we've got that the limit is just evaluated. Okay, but we want to go the other way. How do we know that a function is continuous or not? Well, let's think about all the ways that a function could not be continuous or could be discontinuous. So let's see, I could have a function with a hole in it. That would be discontinuous. It's discontinuous there. Okay, so I could have a hole in it. I could have a function with a hole in it where that hole is plugged, but it's somewhere else. Okay, this is still discontinuous, right? There's this weird thing sticking out. Let's see, we could have infinite rips. We could have a vertical asymptote where they both go to positive infinity. So zoop, zoop, like that. Or likewise, an infinite rip where they go both to negative infinity. Or we can have an infinite rip like we saw last time with 1 over x, where they don't go to the same place. So one goes to positive infinity and the other goes to negative infinity, for example. Or the other way, of course. This one goes to negative infinity and that one goes to positive. Other way. They go to different places. Infinite rip. Or, I think the only other way that a function could be discontinuous is a finite jump or finite rip. So something like that. Okay, so we've got this finite. Here, these are infinite rips. Here we got a finite one. This is called a jump. These are non-removable. The infinite rips are non-removable. And holes, these are removable. Okay, this is an infinite jump as well, but it's a non-removable discontinuity. If we have a vertical asymptote in there, we can't remove it. That's some divide by zero that we're unable to get rid of. Okay, these guys are some divide by zero that we can actually get rid of. That's why they're called removable. Usually it's a zero divide by zero, so we can remove a common factor. All right, so let's see. These are the ways that a function could be discontinuous. So let's see if we can characterize, narrow it down, remove all of these possible ways that it could be discontinuous. If we remove all the possible ways it could be discontinuous, then it's got to be continuous. So let's see, our first criterion. F at A is defined. f at a is defined. All right? F at a is defined takes care of a bunch of these. Let's see. Here, I'm assuming all these interesting places are the A's, right? Okay. Here, f at a, not defined. So this one's taken care of. Here, f at a, not defined. It's infinite. It's not anything definite, right? So taking care of that one. Here, the function value is not defined at a. So we've taken care of that one. Here, the function value is not defined at a. So we've taken care of that one. Now let's see. Here, the function is everywhere defined. So we still have that one. And also here, the function is everywhere defined. Okay, so we still have these two guys to worry about. Second criterion, the limit as x goes to a of f of x exists. The limit exists takes care of this one doubly, right? Here, this doesn't exist because we're going to two different places from both sides, right? This limit is positive infinity, this limit is negative infinity. They're not equal, so that limit doesn't exist. And now this one takes care of this one, takes care of the jump discontinuity, because the limit as I go from the right-hand side is going to be this value here, and the limit as I go from the left-hand side is going to be this value here, but those are not equal. That means that that limit doesn't exist. The right-hand limit exists, the left-hand limit exists, but they're not equal, so that limit does not exist. So forcing the limit as x goes to a exists takes care of our finite jumps, well, as well as this one, but we'd already taken care of that one. It's the finite jumps that we had to worry about. Now, so far we haven't captured that last one. This limit exists, right? As we go to a from both sides, we're going to the same value right here, this L. But here, this is f at a, right? And it's not equal to this L. This limit exists, so it's not jump discontinuity. This limit exists, the function is defined here, but that limit is not equal to the actual value of the function evaluated at that place. So this last one, the last rule takes care of this last situation here. The third criterion is that the limit as x goes to a of f of x is actually the function evaluated at that value. Okay, this third one takes care, the limit exists in this case, of course, and it is actually the function evaluated at that place. The limit exists takes care of this business, but saying that it has to be the function evaluated there takes care of this. That the limit exists, the function is defined, but those two things are not the same. Okay, so this should look familiar. That's the assumption that we can make going the other way. If we know that the function is continuous, then this has to be the case. The function's got to be defined, the function has to exist, and that limit actually has to be the function evaluated at that point. So plug and chug. All right. So these are the three criterion. Again, this is how we're using the limit to define what it means to be continuous. It's kind of a stupid definition, really. To be continuous is to be not discontinuous. Yeah? So that is the definition. Like, here are the ways that we can be discontinuous. If it's not any of these things, then it's got to be continuous, right? And so these three criterion take care of it. The function is defined, limit exists, and it is actually the function evaluated at that place. All right. Sweet. So that's pretty cool. I mean, that was a problem for a very, very long time. Like, how do you actually define what it means? We know that a function is continuous. It doesn't have any jumps or whatever. But that's not really a definition, right? Like, or not really any formal criterion to say, oh, well, it's not discontinuous, or it doesn't have any jumps, or it doesn't have any holes, or, you know, we can take care of that with some specific mathematical criterion and say, if this function meets these criterion using the limit, then we can say for certain, by definition, this thing is continuous. It's not discontinuous. All right. We'll find that the study of calculus, the derivatives in particular, and well, I mean, it's integration as well, but derivatives in particular, that this was really trying to get at the notion of what it means to be continuous and to study continuous functions. All right, so we've defined what it means for a function to be continuous at a point. It's got to meet those criterion. Let's see, f of x is continuous on the interval from a to b. So we've defined what it means for a function to be continuous at a point c. The function is defined at c. It's the limit exists, and the limit is actually the function evaluated at c. Okay, so now we're trying to define what it means to be continuous actually on an interval. And it's kind of dumb. F of x is continuous on AB if f of x is continuous at every c in AB. So it's continuous at every point in that interval, the open interval. And then continuous from the left, that is to say that the left hand limit exists and is the function evaluated at a. So the limit as x goes to a from the right hand side of f of x is f at a. So this is to say it's left continuous. So it is actually evaluated f at a at that endpoint. And likewise at the other side, that my function is actually f at b the limit is actually f at b on the right hand side. So the limit as x goes to b from the left hand side of f of x is f at b. Okay, so we're just taking care of the fact that we're on this interval, closed interval, and we're saying a function is continuous on this closed interval. It's continuous if it's continuous everywhere in the open interval, but we don't have a left-hand side over here because we cut our interval off. So there's no left-hand limit there, and likewise on this side, there's no right-hand limit. And so we say, well, it's continuous going out to here, that our function is actually f at b here, as we go to b from the left-hand side, and that our function is actually f at a as we go to a from the right-hand side. So it's continuous at the endpoints. We just have to take care of the fact that there isn't that other side. Usually we just generally would say it's continuous at every point. It's continuous on an interval if it's continuous at every point in the interval. Okay, so we got that. Now we can define continuity. Let's say a function is continuous on the real line or on some set interval if it's continuous at each point. And now we want to look at a couple theorems. The first theorem that we'll look at looks a little non sequitur right now, but it's very, very useful, and it comes up often in proofs and such. So we want to throw it at you right now. Is the intermediate value theorem, or IVT. If you ever see IVT in a proof somewhere, that's what they mean. Every mathematician would know you're talking about the intermediate value theorem. One note of caution before we start looking at this. This is an existence theorem. It's not going to give you any method or tell you how to find anything. It's just going to tell you that something exists. Okay? Intermediate value theorem is an existence theorem. Now, very often that's useful. Like if we're trying to prove other things, it'll be a step in that proof. So we need something to work with in order to continue on with what we're trying, our series of logic and what we're trying to prove. So we need something. This is one of those things that we might look back to and say, oh, well, this proves that this exists. I have this theorem that says this thing exists, and now I have this thing to work with as I go along in my argument. Okay, it goes like this. If f of x is continuous on interval a, b, and let's say c is some value in between a and b, f at a, no, let's use a y. I'm just trying to make this seem... Okay, so we have some y value. Let's call it a y value since we're used to calling function values y's. So we've got this function that's continuous. These are x's, right? It's continuous on this interval from a to b. And we have f evaluated at a and f evaluated at b, and some y value that's in between those, okay? There exists, that's a backward capital E. This is the existential quantifier. It means there exists, backward capital E. There exists some C in that interval. So there exists C in, the symbol for in is this curvy E, or is an element of some set, right? We're talking about this set, this interval a to b. So there exists some C in the interval a to b, which is the same as saying a is less than c is less than b. The C exists in that interval such that f evaluated at C is the y value. That's the intermediate value theorem. If that function is continuous, it doesn't jump around is what it's saying. We've got this continuous function. If I have some y value in the interval between the one endpoint and the other endpoint, it had to pass through every value in between, at least once, right? So here's my, let's say here's f at b, it's some value, and here's f at a, some other value. And I'm saying there's some y value in between there, right? There's some y value in between there. Well, if at a f was here, and at b, f was here, and it's continuous, it had to pass through every y value between f and a and f at b, right? At least once. Maybe more than once. Maybe it did a bunch of this business. I don't know. Maybe it passed through some points more than once. But it had to pass through every point at least once. So there has to be some c in between a and b. Some c in between these a and b's, such that that function value evaluated at c is this y. There's somewhere in that interval where it had to hit that y value. It couldn't jump over it, is what it's saying. Okay? So it doesn't tell us how to find that c. It doesn't give us any method or anything. It doesn't tell us what that c is. It just tells us that that c exists. We know that it exists. Okay? Usually, the most frequent use of the intermediate value theorem, the easiest way to apply it, is to prove the existence of a zero. Now, usually we're very obsessed with finding zeros of functions, right? So if I want to find some zero in some interval, it might be a good idea to at least know that that zero exists somewhere before I try to start looking for it, right? So very often, the way that this plays out is to prove, like I say, the existence of these zeros, and we won't even care what the value of the function actually is, right? If f at a is less than 0, so I don't even care what its value is, it's just negative, and f at b is greater than 0, again, I don't care what it is, it's just some positive value, then, well, and f is continuous, okay, f is a continuous function, f at a is negative, f at b is positive, then for absolute certain, if it's continuous, it didn't jump over 0. In order to go from negative to a positive value, it must have traveled through 0. So there exists some c in that interval between a and b. There's some value, some x value in there, such that f at c, the function evaluated there, is equal to 0. That's the most, it's the simplest application of it, and it's the most common, is usually just to prove that there is a 0 in that interval. Right? Say, okay, if I'm challenged with finding a 0 of a sine function, say. Finding a 0 of a sine function. And I say, well, okay, the sine of negative pi over 2 is -1. I don't even care that it's -1. I don't care what the actual value is. I just care that it's negative. But okay, sine at negative pi over 2, -1. The sine of pi over 2 is 1. Again, I don't really care about its value. I just care that it's positive. But fine. So it's -1 at negative pi over 2 and +1 at pi over 2. Sine function is continuous. It must have passed through 0 somewhere in that interval. There exists some c in the interval between negative pi over 2 and pi over 2, such that the sine of c is 0. We know that a 0 of the sine exists in that interval. because it went from negative to positive. It's a continuous function, so it had to pass through 0. Okay. How this ultimately very often ends up playing out is we'll have some situation, like say you're running a company or whatever. You always want to minimize your costs and maximize your profits, minimize the amount of surface area, so the amount of material you need in order to maximize the volume of, say, some box that you're shipping stuff in. Optimization problems. We don't ever want to just half, oh, I'd like to make quarter as much profit as I possibly could, right? No, of course not. I want to make as much profit and minimize my cost, optimize my company, right? So if we're looking for maxes and mins, this is one thing to notice. If I have a max, the change tops out. The change goes from positive to negative, right? My slope here is positive. This function is increasing. My slope here is negative. The function is decreasing. So here my slope is positive. Here my slope is negative. That means that there's some place in here where that slope is 0. And funny enough, that happens to be exactly at the maximum. Right where it tops out, that slope is 0. Likewise down here. The slope here is negative, right? The function is decreasing. Slope here is positive. Function is increasing. That means somewhere in there, there's a place where the slope is 0, that there is no change at all. It's not decreasing or increasing at all. And that'll be the min. So maxes and mins always occur where that tangent line is 0. That's a pretty handy tool. And we can use the intermediate value theorem here to say, oh, well, I've got this continuous function. If the change goes from positive to negative, it's got to be 0 somewhere. So there's a max in there, or a min maybe. So if I'm trying to optimize my company, this is going to tell me, okay, I can look in this region and I'm going to be able to find an optimization. I'm going to be able to find a max. Maximize my profit or whatever it might be. Okay, so that's sort of how the intermediate value theorem plays out as we go along. It's proving the existence of that place in that interval where we can get some certain value. Usually it's a 0. That's the most interesting information that we're almost always after, right? Is where is a function 0? So, and it's simple to do that way since we don't need to worry about what the values actually are. We just need to worry about their signs. Okay, so that's the intermediate value theorem, IVT. And we got one other that we want to look at right now, which is the squeeze theorem. Squeeze theorem. And it's really called that, and its name actually sort of means what it's doing. So we're going to have two functions, f of x and g of x. So let f of x and g of x be continuous on an interval a to b. Except possibly at c. Except possibly at c, where c is some value in between a and c, b. So let's just say that a is less than c is less than b. So c is some value in that interval. And f of x is greater than or equal to g of x. And the limit as x goes to a of f of x is L, and that's equal to the limit as x goes to a of g of x if f of x is greater than or equal to h of x is greater than or equal to g of x. Yeah, I had f greater than g, okay. So h is some function in between these two guys. Then the limit as x goes to, I used c. Yeah, because I already used a in my bound, okay. The limit as x goes to c of h of x is L. Okay, there's a lot of assumptions and stuff going on there. A lot of let this and this and this and this and then and if. So let's draw a picture and see what's happening. We've got f and g. They're continuous functions on an interval a to b. So we've got some f. And let's say here's a and here's b. Just arbitrary. It's continuous on this interval from a to b, except possibly at some c. Let's say there's a hole there. This is my f, yeah. Got this continuous function f on the interval from a to b, except possibly at c. And we have this other g of x. Got this other g of x, also continuous on the interval from a to b, except possibly at c. And we have that the limit as g of x goes to c is equal to the limit as f of x goes to c, which is this L value here. Okay, so we got these two continuous functions. F is greater than g. Now, if we have some h that's in between them, so f is greater than h, greater than or equal to h, here's my h. So h of x is in between f and g. Then the limit of h has to be L as well. We're saying that here I have this function and this function. They're both going to the same place. They have a limit. It exists and it's the same. So if there's any function that's trapped in between them, it gets squeezed, right? That here's my f is greater than g. If my h is in between and f and g have the same limit L here, then h has to have that same limit L as well. It gets squished. So this is a way for us to use known limits to get at other limits that we don't know. Say, for example, if I'm looking at, I've got some function like this. Well, I need the absolute value in order to do that, but let me put it up a little bit just so we don't have to worry about absolute value. Like that. Okay. So I have one function, y equals 0, this x-axis, right? Y equals 0. Well, what's the limit as we go to infinity of 0? Well, it's just always, as I go along, it's just always 0, 0, 0, 0, 0, 0, 0, forever, right? Just always 0. Okay, so we know that the limit as x goes to infinity, it doesn't matter where x goes, of a constant 0, y equals 0, is just 0. Now, let's say this was the function 1 over x. 1 over x. As we go to infinity, that's going to get closer and closer and closer and closer and closer to 0, right? It'll never actually touch 0, but if we were to go all the way to infinity, it would be 0. Here's that double speak again. It's getting closer and closer and closer to 0 than any value we could ever pick. That's how we'll do it formally, in fact. We'll say, okay, 1 trillionth. And I'll go, nope, it's closer than that. Here's the value that gets you closer than that. You go, oh, okay, I was just kidding. 1 over a Google. Nope, here's the value that gets you closer to 0 than that. You go, any value you want to give me, 1 over a Googleplex. Nope, here's the value that gets us closer to 0 than that. Right? So regardless of what value, what distance you want to give me, I can find some place along here that 1 over x is going to be closer to 0 than that value. I can get as close to 0 as I possibly want. So the limit there of 1 over x is 0. So if I've got this other function, whatever it might be, this h, and I know that h, this weird curvy thing in here, it's always greater than 0, so it's strictly positive, and I know that it's less than 1 over x all the time. See, it just wobbles in here. It's going to get squeezed. The limit as x goes to infinity of h of x has to also be 0. Because this limit is 0, this limit is 0, and the function is in between those. So bam. Or if we go to someplace finite, it's the same exact idea. If those two things are going to the same place and we've got something in between, it has to be going to the same place as well. That's the squeeze theorem. So let's use that. Let's apply it to the one I showed you last time. This is a really, really important limit. It pops up in some major places. The limit as x goes to 0 of the sine of x over x. Okay, we talked about this one last time. It's a really, really important limit, but there's no algebraic out. There's no tricks we can pull because of that transcendental there, that sign. We're stuck. We can't pull the x out and simplify, or it's not, sine of 1 or anything like that, right? So we're really stuck here. This is 1. All right? Now, if I take the ratio of two things and their ratio is 1, that means they're the same. Right? That's what it means for the ratio of two things to be 1. They're the same thing. So what this is saying is, if we get really, really close to 0, the sine of x, this curvy function, and the line y equals x, the straight line, they look identical. They're exactly the same thing. So if I blow this up, sine function is negative over here and comes positive, is 0 at 0, and comes down like this, right? And the line y equals x is a straight line like that. Clearly, these two things diverge the further away that we get from 0. They move away from each other and then really diverge, right? This thing is just going to oscillate, and that thing will go off to infinity forever. But as we get closer and closer to 0, you see they look identical. They're almost exactly the same thing. And this is what this is actually saying, is that if we go to 0, the sine and the line y equals x, they are the same. Their ratio is 1. Okay, so let's prove it. Okay, so I'm going to start with an observation. I'm looking at unit circle, some theta, some angle theta. Since I'm going to go theta, because we are talking about angles here, it doesn't matter, but just to be consistent. Then this distance here, the opposite side, that y value, is the sine of theta, right? The unit circle, our radius is 1. That's why we do that, is so that the sine is y. In radians, the angle measure is equal to the arc length. So this theta is this curve. Well, clearly, for all thetas in between 0 and pi over 2, the sine of theta is going to be less than theta, right? The straight line, we've got this curved line. That curve is going to have to be longer than the length of the straight line. So we have that the sine of theta must be less than theta. Also, we have the tangent. This line, you may or may not have ever seen that. That's the secant. Sect means to cut, so the secant is the cutter. It cuts off the tangent, which is this length. Tangent of theta, here, right? It's tangent to our unit circle. Cotangent is up this way, across the horizontal. So there's our tangent, and we can observe that on this interval, this tangent line has to be longer than this curve, right? So I'm just making an observation on the unit circle. Sine of theta has to be less than theta, and theta has to be less than the tangent of theta. Okay, so there's my inequality that I'm going to start with. That's just looking at the unit circle and observing the lengths of those lines. Sine of theta has to be shorter than theta, and the arc length there has to be shorter than the length of the tangent. Now I just divide everything by sine of theta. Oops. Divide, so 1 is less than or equal to theta over the sine of theta. I'm getting close, right? I want to look at sine theta over theta, so I got theta over sine theta. If I take the tangent and divide by sine, I have sine over cosine, so this I'll have 1 over cosine. Sine over cosine simplifies to 1. And now, like I said, I'm close. I've got this theta over sine theta. I want sine theta over theta, so I'll just take the reciprocal. But if I take the reciprocal in an inequality, we have to flip the sign. So 1 cosine theta is less than the sine of theta over theta is less than 1. So I took the reciprocals of those, but when I did that, I had to reverse my inequalities. So that's why this cosine comes over here and the 1 goes over there. Now, let's look at the limits. The limit as theta goes to 0, because that's what we're interested in, of the cosine of theta, well, the cosine is a continuous function on the entire real line for all theta. So that's just the cosine of 0. Cosine of 0 is 1. Over here, the limit as theta goes to 0 of 1, well, that's just a constant. It doesn't matter where theta goes. It's always just 1. So we have that the sine of theta over theta is in between 1 and the cosine of theta. For all values, they're in between. That the limit of the cosine is 1, and then the limit of 1 is 1. So this is getting squished. It's getting squeezed, right? So by the squeeze theorem, therefore is 3 little dots. By the squeeze theorem. So that's the theorem that we're using to justify our conclusion. It's the squeeze theorem. We've got that the limit as theta goes to 0 of the sine of theta over theta is 1. And we've proven that using the squeeze theorem. It got squished. So essentially, here's my 1. As we go to 0, my cosine is going to 1, right? And we're saying that the sine of x over x, or the sine of theta over theta, it doesn't really matter what it does, but it's somewhere in here, right? It's in between 1 and the cosine of theta. So as we go to 0, regardless of what the sine of theta over theta does, it has to get squished, and it has to be 1 at 0. All right, good.